These are the AP review questions for our Chapter 11, 13 AP test. So let's take a look at some multiple choice questions. We have a graph which we'll use for the next three questions. The graph here is of the compound methane, CH4. Right away, recognize that CH4 is a nonpolar substance, so it should have pretty weak intermolecular forces. It's also a pretty small molecule. And we have a heating curve for it. Remember the 5 parts of a heating curve: heating the solid, melting, heating the liquid, boiling, and then heating the gas. The first question asks us how much energy is required to melt 64 grams of methane at 90 K. So melting is this portion right here, and heat of fusion tells us how much heat is required to melt an amount of a substance. In this case, we're given kilojoules per mole, so it takes 0.49 kilojoules to melt every mole of methane. We're told we have 64 grams. We're also given the molar mass, so that we don't spend as much time calculating it. And really, it's a matter of how many moles we have times what the heat of fusion is. Remember, to find heat in this portion of the graph, you take moles times your heat of fusion. You could also do sometimes grams. Sometimes this is represented in grams, but in this case in moles. So we'll use moles. We first have to find moles. To find moles, we take the mass, divided by the molar mass. We usually do it like this. We put a mole on top, and then the molar mass on the bottom, 16 grams of methane. Essentially, we're dividing 64 by 16. Now, I should say that this is a multiple choice question, which does not allow you to use calculators. So you actually have to divide 64 by 16 in your head, or in some sort of way. You may recognize that 16 times 2 is 32, which means times 2 is 64, which this gives you 4 moles. And it's a matter of multiplying 4 moles times heat of fusion, which is 0.94. 0.94 is pretty close to 1, so we're going to still end up with about 4 for the kilojoules, and the closest answer to that is B. So we're almost at 4 kilojoules. Sometimes these multiple choice questions are easier done if you guesstimate the answer, or faster done, I should say, if you guesstimate the answer. The answer is B in this case. Take a look at number 2. Number 2 asks a theoretical question, and it says, which of the following best explains why more energy is required for the process occurring at 110 than for the process occurring at 90? At 110, here, we have vaporization happening. At 90, we have melting happening. So you'll notice that the vaporization portion of the heating curve is longer. This is because it does take more heat to vaporize a substance than it does to melt it. We just have to find the appropriate explanation. And the best explanation is actually the first explanation. Intermolecular attractions are completely overcome during vaporization. This is true in a gaseous state. There are no attractive forces. Remember, a liquid and a solid has attractive forces, but a gas does not have any attractive forces, which means you have to completely remove or completely break the bonds. So A is best. B says intermolecular attractions in the solid phase are weaker than in the liquid phase. This is actually, although it sounds like it's true, it is not. Both in the solid and in the liquid phase, there are intermolecular attractions, and the attractive forces between molecules are present in both cases to the same extent. Electron clouds of methane are molecules are less polarizable at lower temperature. This is not necessarily true, so that one's out. These are out. D says vaporization involves a large increase in temperature. Not necessarily. You have to increase the temp to get to vaporization, but the vaporization itself, there is no change in temperature. So none of the rest of the answers are as good as the first answer. Number 3 says the enthalpy of vaporization of water is about 40.7 kilojoules per mole. Which of the following best explains why the enthalpy of vaporization of methane is less than that of water? So we saw that methane is quite a bit less. We recognize that water, being polar, actually has dipole forces operating in it, but it having hydrogen bonding is why the vaporization for water is so high. So actually, anytime you see hydrogen bonding, that will likely overcome any other intermolecular force. Now, size also matters. So if you have a substance that's quite a bit bigger than water, then it could have overall stronger forces. But water versus methane is actually about the same size as water. And actually methane's mass is about 16, we saw, grams per mole. Water's mass is about 18 grams per mole, so they are comparable in their size, which means any other difference will make water win. So water's hydrogen bonding actually wins. So even though methane has a smaller mass, that is not the reason. Methane has weaker dispersion forces, not necessarily. Methane's actually slightly bigger, but methane has lower density. That is true, but it doesn't explain the fact. Good. Number 4 then says substances with greater intermolecular forces of attraction, what we've been studying in this chapter, have, number 1, higher boiling points. This is true because the stronger the attraction, the more energy you must put in order to separate that attraction. Greater viscosity, this is also true. Liquids will tend to be thicker if they have stronger dispersion forces. That's because the particles are more strongly attracted. Greater amount of surface tension, this is also a physical property that increases with intermolecular forces. Higher vapor pressure. Okay, higher vapor pressure is actually wrong because if a substance has strong intermolecular forces, then it will not vaporize as easily. So it will have weaker or smaller vapor pressures. Then absence of crystalline structures, this is not true. Crystalline structures, crystallinity applies to all substances. You can actually crystallize molecular compounds with different forces. So we should pick the one that says 1, 2, and 3 only, which is, part C, apologize there. That should be C. Okay, and then we have the last question here at the bottom, number 5, which tells us, in the evaporation process. This was a bit tricky, and I don't know if we talked about the details of the evaporation process. But let's pick the best answer. A, all molecules tend to evaporate spontaneously. This is not necessarily true. So you have a beaker of a liquid. It turns out that the molecules that are the hottest, with the highest kinetic energy, will be the ones that evaporate. So technically, even if you are at room temperature, at room temp, which is, you could say, 22 degrees Celsius, even if you're at 22 degrees C, evaporation still happens because most of the molecules in the beaker are cold or room temperature. Some have enough energy, some are hot from the constant collisions that happen. Some molecules can attain enough energy then to escape, and that's why evaporation happens under or any temperature below the boiling point. So the hottest molecules, however, are the ones that evaporate. So only low kinetic energy molecules can escape. That is incorrect. The temperature of the remaining liquid falls. This is actually correct. This is weird, but what happens, since the hottest molecules are the ones that escape, the molecules left behind are colder. And if the evaporation process happens quick enough, you can actually check the temperature of the liquid decreasing. The temp will actually go down if this happens quickly enough. And I think we've demonstrated that in class for you, but if not, we'll be happy to oblige. So the liquid temperature does not rise, it falls. Condensation and evaporation rates will be the same. That's only if this is a closed system. But then evaporation will stop. So actually, this is also incorrect. So some examples of multiple choice questions that you may find on the upcoming chapter 13 and 11 tests.